Good morning.
Good morning. Good morning. How are you?
Good.
I predict that we'll have a good attendance today. Let's see here. What is going on in the chat? Good morning, Dylan.
Good morning, Dr. Joe.
Okay. So what are we going to do today? I was thinking we could talk about Fourier Transform spectroscopy, like FTIR, etc. What do you think?
Exciting.
Yeah, I
I
think
keep
that'll be
reading
good.
about it. It'd be nice to learn about it.
Yeah. Good. Excellent. Well, let's have a good conversation. I think it can be fun. So let's see here. Let me get this guy out. Put this guy down here. Put this guy up here. Good morning, Brandon.
Good morning, Dr. Charles. How are you doing?
I'm doing fine. It's nice to have people back after Chem is over and stuff like that. But I have decided, me and Cindy have decided to talk about FTIR today. What do you think?
I think that sounds fine. Since you've gone through most of the homework already, I think we're good on that.
Yeah, it's a little bit out of order, isn't it? Oh well. You know, and to be honest, I'm still puzzled by the questions that they were asking. But they're easy enough to sort out, but I'm like, I've never really thought about it this way. Like, for example, there's a thing about you take the difference in the centimeters between samples and you flip that over, and that's like the entire spectral range in nanometers or something, or centimeters. I don't know. That's kind of weird. Or in wave numbers. Anyway, shutting up now. Let me share a screen here with some information on it that actually might be useful. Yay! So, first, a couple general thoughts about FTIR. FTIR is, you know, it's like not the way that IR used to be done. You know, IR spectroscopy used to be done the same way that UV vis is done. You know, with a grating. Oops, hold on just a sec. But I think there were a lot of clever folks out there who realized that you could just do much, much better by using an interferometer. And an interferometer, it's just a box, you know? And what the box will do is it will modulate the light that you put into it. So the modulation is taking a particular frequency of light, you know, and then turning it on and off at a certain frequency, you know? And the way the Michelson interferometer works, the one they use in FTIR, is that the low frequencies of light are modulated at a low frequency. So as a matter of fact, I think there's a thing where like there's it's like C over V or V over C or something, where you can take the mirror velocity, and the mirror velocity and the speed of light, they combine to tell you how fast that that light frequency will be modulated. And it so happens that with a millimeter per second or so, or maybe a centimeter per second or so of mirror velocity in an interferometer, that takes the mid-infrared frequencies down into the audio spectrum. So what that means is it'll take 3,000 wave numbers, and that might be 10 kilohertz, 10,000 hertz. And 10,000 hertz is something that we're very skilled in dealing with, that frequency range, these, these types of frequencies we can manage. So let me draw a little picture for you. Hold on just a sec. I've also got allergies super bad, so I'm sorry. Okay, so let me forget where I do the share thingy. There it is. New share. Oh wait. Cancel that. There we go. Okay, so essentially the way a Michelson interferometer works is, you have a light source, and then the light source shines into the interferometer. And then what happens is that every light frequency comes out at the same time, but each light frequency is modulated. So what comes out is a pattern of light that has all these frequencies summed up in such a way that they make what's called an interferogram. Sorry, guys. So this is an interferogram. right? And so, and the interferogram, it's just a funny combination of modulations of light intensity. And so the idea then is that, then you have, then you can have a sample, and a detector, and then you need a PC to do the Fourier transform. And the Fourier transform will turn the interferogram back into an intensity versus frequency plot. So, and then everything else is done the same way. We take the sample, spectrum over the blank spectrum, and then that gives us a transmittance spectrum. And then from transmittance, if we want to, we can compute absorbance, Oops. But really the only difference here is the combination of the interferometer and then the Fourier transform. And so the interferometer is really a modulator. And it means that the detector here, at any moment in time, it's seeing all wavelengths, sees all frequencies at the same time. Sees means it detects all frequencies at the same time. And then how it deconvolutes them is the Fourier transform. So so let's go ahead and see how the Fourier transform works, and we'll talk about this a little bit more. So so here's a mathematical description of the Fourier transform, right? And this to me is cart before horse, right? So this is the last step after the computer gets your spectrum. It does a computation, and it calculates a spectrum here, right? Y is intensity and X is frequency here, right? And sorry. So you can see like how let me see if I make sure I get this right. The light that goes in, you collect it as a function of time. Time or retardation. Retardation is the displacement of a mirror in the interferometer, right? And then what the Fourier transform does is it inverts the units on the x-axis, right? So what went in as centimeters comes out as reciprocal centimeters. And that's probably the origin of using that unit in chemistry. So if you take a if you take data in as a function of retardation, like 1 over x, what you'll get out of a Fourier transform is a set of coefficients a0 and b0 and a1 and b1, right? And a2, b2, a3 up to n, right? And n is probably the number of data points in the data set. And I actually had to make a correction to the foils here because Harris had this as some weird thing here, but the fundamental frequency omega is equal to 2 pi over the entire mirror travel here. I think anyway. You know, fuck it, I'm not sure about that. Damn it. Okay, let's just get rid of this motherfucker for a while. Sorry about that. So in any case, you've got a fundamental frequency here. And then harmonics of that fundamental. You got 0, right? It's funny because A0 times sine of omega times 0, right? So the argument sine of 0 is 0, right? So this term never matters. This term is always 0. It's kind of weird, right? And this term is always just B0, right? Because the cosine of 0 is 1. So then the first term is just always B0, right? But then these guys all have some magnitude, A1, B1, A2, B2. And then you basically, you plot these guys versus omega, I think. Why is my memory so shot right now? Hold on. So, oops, let me see, make sure I'm not muted. Okay, so figure 2029 here is what I'd like to focus on. And basically what this guy says is that, you know, if you have data, right? If you have two peaks that look just like this, you know, this black curve, right? And you Fourier transform that data, then inverse Fourier transform. You know, you're just doing a stupid exercise. You're transforming it into new domain, then you're back transforming it back. But you do so with only three terms, a 0, a 1, and a 2. What you'll get back from this is this horrible representation of two peaks, which really only has one peak, right? But if you add more and more, if you add just 8 terms, 8 sine terms to this, then you can get a decent representation of these peaks. So, you know, it'd be the cosine term, then a sine cosine at 1, sine cosine at 2, sine cosine at 3, and you add all those terms up, and then you'll get this original spectrum back. So this is sort of trying to prove to you in a backwards way here that the Fourier transform works as a mathematical tool if you have enough terms in it, right? So in this 3-term guy, you can see what looks like sort of a sine curve here, right? In this one, you can see a more sine curves, right? And in this one, you really can't so much see the sine curves anymore. You can just see these Gaussian curves. And then, you know, a typical Fourier transform might have 4096 actual terms in it. So, so here's how that happens. This is how the interferometer works. This is how the modulator works. And what it's going to do is it's going to take the light in, it's going to modulate it, and then you'll have a sample in and a sample out to get a blank and a sample, right? Then you'll have the detector here. And in each case, the detector is going to collect a modulated light spectrum. Then it will transform those into a new domain that's light intensity versus frequency, and then calculate the absorbance or the transmittance or the absorbance from those. So how does it work here? Well, the modulator part. The modulator part works with a beam splitter. There's a source, and the source shines on the beam splitter. And at the beam splitter, there is a portion of the beam that is deflected to a stationary mirror here and back down. And then let's focus for now on the portion of this beam that takes this path. It goes over, bounces off the beam splitter, comes up to the mirror, comes down, goes through the sample into the detector, right? Then there's another portion of this beam that comes, it passes through the beam splitter, hits this mirror, comes back, hits the beam splitter, passes the sample into the detector, right? So by the same arguments that we used with diffraction gratings, you know, if there's a path length difference between, say, here OS and OM, right? Or whatever this symbol Q or O or whatever this is, right? If there's a path length difference, then a given frequency of light will sum together at this point in a different state of self-interference, right? The beam will interfere with itself, and then depending on the relationship of delta, which is the path length difference, and lambda, which is the light frequency, a given light frequency will either be in phase or out of phase with itself, right? And this is one of the keys here, is that you have to think of the wave as literally splitting in a coherent way. And that's what happens somehow. I don't really know how. But there's a given wave that leaves the source, and that wave is split and recombined with itself in such a way that, for example, if you have a laser, a single frequency light source going in here, the interferogram that it produces is this beautiful sinusoidal or cosinusoidal wave, right? Where when delta is 0, it's high. When delta is lambda over 2, it's low. And then lambda, lambda, da, 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 right? And so what you do is you just move this mirror back and forth, right? And then you monitor the intensity of the interferogram. And then the interferogram itself, let me take a little sideways jog back to the document camera, and then I'll do something there. So the interferogram itself is normally complex. So and so if you have with monochromatic light, what you'll see is the intensity of the light that comes out versus the retardation, the mirror movement here, will look like a pure sinusoid, right? That's with monochromatic light in. With polychromatic light, what you'll see, however, is something quite different. That's where the intensity, it's around an average value here. And there's little ripples. And then it looks like this, right? And this peak here is called the center burst. And the center burst is actually used, this point here is used to define delta equals 0. Otherwise, that value is unknown. So this is single frequency in and a single modulation out, right? And this is many frequencies in and many modulated frequencies out. all piled on top of each other. Okay. So, I'm dancing around a little bit, and I'm pretty sure we're going to come back to this, so don't despair. So the interferogram, if it's monochromatic light, it'll just be it'll just give this type of a thing here, 2 pi delta over lambda, right? And then B is just some intensity factor. But so here's an interesting case, right? If you have one frequency coming in, right, then you'll get one interferogram coming out, right? Or you get one frequency coming in, and then the interferogram will clearly just consist of this one frequency, right? So here we've got every centimeter of retardation, we get 1, 2 peaks in the interferogram. That corresponds to a frequency of 2 per centimeter, right? And then here we have the same 2 plus 8 per centimeter. So we've got the same 2, but then we got 1, 2, 3, 4, 5, 6, 7, and 8, So this is a perfect 2 plus 8, So this is how these are going to add up. This is just 1, this is 2. Oops. And that's the same gosh damn 2. And, and then after a while, after you put thousands of frequencies in, then what you'll get is sort of an average voltage here. And then you'll get all this complex, noisy looking crap, including a center burst and maybe a center dip, and then more on the other side, right? And when you Fourier transform this, it's going to give you a light intensity spectrum, right? Just the same way that if it had gone through a monochromator, right? You'd have something that looks really similar, right? And then you collect a sample, right? And then you transform that, and you'll get something that looks different here. It'll have some missing peaks. And then you ratio these two guys, and that'll give you your transmission spectrum. And I hope to God that your transmission spectrum looks better than this one, because this is a mess. I mean, this is the horriblest transition spectrum I've ever seen. But here we go. Percent T is equal to P over P0, right? There's P, P0 times 100%, right? And and here it is. It's like you can improve the signal to noise generally by adding more together, And sometimes you get a wiggle frequency in there that's actually in the sample. If you've got a thin film in the sample, that can give you another type of interferometry happening. But in any case, you get this transmission spectrum, and then you can work with that. So let's go through a couple of the couple of aspects of this process. I'm going to go back to the document cam, and hopefully I can pull something out here. So these are used to diagnose and fix the interferometer, right? And typically in an instrument there is a laser beam, and it actually goes alongside the sample beam, and so the laser beam is not analyzed for its light absorption. However, it's only used as a clock, and so the laser, you can typically they use a red laser, right? And the red laser goes in, and it just creates this interferogram. And then, so at what frequency these peaks are coming, and you actually lock the mirror travel onto that interferogram. So the mirror has to go back and forth, and that's one of the disadvantages of the FT method, is that there literally is a sliding mirror. There's a mirror that travels back and forth. And so that's a little bit of a disadvantage, the mechanical part of it there. But they actually happen to be extremely accurate in terms of frequency, because they lock onto the mirror movement using a laser, right? Using a very consistent frequency laser. So, and then when it's transformed, it becomes a center burst thing. And then, or I'm sorry, it's not transformed. This is the raw data. This is raw data. And then this is transformed by a Fourier transform. And this gives you a power spectrum. And instead of delta, you get 1 over delta here. And 1 over delta is actually inverse centimeters, right? And the light frequency nu bar is equal to the mirror frequency V. I think it's divided by C. Something like that. Hold on. Let's just think about this for a second. The light frequency is related to the mirror velocity, right? And this is going to be centimeters per second. And so Oh gosh, I'm not going to be able to pull this out. I have such good notes on this. But it's just not emphasized by Harris. So I think I'll just kind of leave this be, right? The light frequency is proportional to the mirror velocity, right? And I think I'll just cut to the chase here, right? And let's talk about the advantages of doing spectroscopy using an interferometer as opposed to a monochromator, right? So let's talk about one of the main advantages is that you never throw away any light. You always use all light. Right? And then, and this is called a multiplex advantage. So basically, you conserve photons, you know? Right. And let's just leave it here. That the main advantage of FTIR is this multiplex advantage. So if you have a whoops. So if you have a weak source, which is typical of FTIR, a flaky detector, then this really helps. All right. So I have to take a 5-minute break and then I will be right back. So, I guess we'll go with sort of talking about the similarities between interferometry and normal spectrometry just for a minute, and then we can move on to Savitsky-Golay. But you know, there's you know, if you have a white light source, right? You know, basically what you have is EM waves of many frequencies, and they're all added and they're all summed up, right? You know, and spectroscopy is taking these and saying, well, what is the response to this frequency of light? You know, and this makes a spectrum, and then what we do is, you know, we plot the absorbance versus the number. You know, 1, 2, 3, 4, 5. You know, we make a spectrum. You know, of these amplitudes, you know, versus these frequencies. And the monochromator does them one at a time. That's kind of like how our carry 60 or carry whatever one works at scans, and it reports the absorbance or the intensity at each wavelength one at a time. Then there's a polychromator, which essentially it spreads the, or let's say it uses 4096 detectors in an array and gets 4096 at a time, you know? And then there's also an interferometer, which gets all frequencies at a time. But it relies on the idea that every frequency will be modulated uniquely, right? So and let me see. And I forget exactly how they're modulated down. It's something like C over V or something like that. But so let's see. I wonder if you can read this. And so the interferometer, it has some advantages of the polychrometer, you know, but it's just it works well for broad beams that are hard to focus, actually, and it works well for weak beams, you know, hard to detect beams, things like that. So I think that's all pretty much I have to say about interferometry here. And I can move on to Savitsky-Golay, you know, type things, but I should probably, why don't I briefly mention some types of noise? For example, you know, there's, you know, the general idea that signal averaging can improve the quality of the data, right? So long as the data is not changing with time, you know, as long as the data is just repeating over and over, if you average it, you'll get a better look. So, for example, this light spectrum here, if you sample it just once, you get this noisy representation of it. Then you average 4, 16, 64, and 256 times, and the signal to noise ratio improves each time. And so essentially what happens is you know, you could treat this like A bar here, and this is like A, and you could look at the RMS difference between this and this guy here and add them up and square root them. This will give you the RMS noise. But the idea here, and the only thing that we'll really care about, is that the signal to noise ratio improves as the square root of n. So when we go from 1 to 4, the square root of 4 is 2. And so the signal to noise ratio doubles going from 1 to 4. And then from 4 to 16, 16 over 4 is 4. So this also, the square root of 4 here, the square root of the ratio of these two is 4, is 2 rather, because 16 over 4 is 4, square root of 4 is 2, right? So the signal to noise ratio doubles each time we move up here. So 16 times 4 is 64. So signal to noise doubles. 64 times 4 is 256. So signal to noise ratio doubles. So in going from 1 to 256, we get 2, 4, 8. We get a factor of 16 improvement in signal to noise for you know, a factor of 256 improvement in sampling, in oversampling. And this idea works well to a point, right? So we can go an order of magnitude improvement in signal to noise ratio, but then things start to go haywire, and this type of a curve actually doglegs when you get to really ridiculously long times. And that's because there's changes in line frequency and temperature and God knows what that start to erode signal to noise ratio after a long, long time. So, so uncertainty will start to increase, and that the increase is due to what's called drift. And so there's so there's white noise, drift noise, and line noise as an example. White noise is always present, and it can be improved by oversampling. Drift noise can definitely be improved via oversampling until the frequency gets so low, the amplitude gets really high. So at very long times, very low frequencies, this drift noise becomes kind of impossible to deal with, right? So you have to be careful about averaging for long, long, long times. And then line noise is things like power lines at 60 hertz, computer monitors, and things like that that have sustained frequencies of noise, And monitors probably don't have that anymore. They used to. Dating myself. Okay, so you can. Shit, I don't even want to talk about this. Let's talk about a Savitsky-Golay smooth, right? And I have an example of that for you to sort of round out the hour with here. You can, if you don't know what a moving average is, right? You can take a signal like this, right? And you can improve it cosmetically. And I say cosmetically only because whenever you do smoothing, digital smoothing, you remove information, right? You actually remove information from the original signal, right? But cosmetically, maybe it's going to look different, right? So a moving average is the bluntest tool you can use here, right? And what a moving average does is it takes, say, 10 data points, and it averages all 10 points, and then you place that 10-point average on a new on the scale, right? But this is just the average of the 10 adjacent points. Then you move the frame of the average over. So like, for example, you might start with points 0 through 9, or say 1 through 10 here, right? Or 1 through 9, for example. Average them together and plot them at 0.5. And then you can take 2 through 10, plot them at 0.6. And then 3 through 11, plot them at 0.7, etc., right? And so that will squish down the noise a little bit, but it will tend to broaden the peaks, right? So this guy actually has the most information, but if you want a more cosmetically appealing peak, you can do a moving average here, right? It's called a moving average. A Savitsky-Golay is a different kind of moving average, right? So let me pull out a Savitsky-Golay for you in Excel, and I can show you how that's done. So let's see here. I'm going to do a new share. Da-da-da. And so here's a Savitsky-Golay, right? I've got original data that I just took from the book, right? And that's these blue dots, right? And the blue dots are then averaged by Savitsky-Golay over the points, for example, 0.1, 2, 3, 4, 5, 6, 7. These points are averaged together in a special way, in a special weighted average, right? And the weights are 7, 6, 3, and -2, and 7, 6, 3, and -2 on either side of the points, right? So that means that the first 3 points here are lost when we do this Savitsky-Golay, because it has to reach out 3 points to lower and 3 points to higher energy in this case. The x-axis value, and then they're divided by the norm, the normalizing factor, which is just the sum of these coefficients, right? So, so this is B2 times SG1 times -2 plus B3 times 3 plus B4 times 6 plus B5 times 7 plus B6 times 6 plus B7 times 3 plus B8 times -2. These are all added up and divided by 21. And that's how this works. Then on the other hand, if you want to just boxcar average or moving average, then you just take the equally weighted average of every point here, and you report that. And so that will give you this green line. So that's all you have to do, to get the Savitsky-Golay, is you just have to program in something like this, and then the averaging window moves with the data. So is that more or less clear? Clear as mud? Hopefully. I'm sorry. It's so boring today. I'm just like tired. I don't know what's wrong with me. And it's probably not even me. It's probably just like stupid chemistry world nonsense. Somebody say something, please.
Hello.
I feel lonely. Hello, Fook. How are you?
I'm steady. How are you, sir?
You're steady or you're studying?
Both. Kind of both.
You're steadily studying.
Yeah, I multitask all the time.
All right. All right. Yeah. Okay. How are you, Casey? Are you awake yet?
No.
No? Not awake. Oh gosh.
At least her
How about you,
internet's
Cindy?
working today.
It is.
Yeah. That's good. That's good. That's good. That's good. Oh, I forgot. Here, I've got a coffee too. Oops. I've got a
I have
coffee.
tea, non-caffeinated.
Yeah. Yeah. It's like right around this time of the week, I start to resent caffeine because it's like I don't want to be awake, Just go away. I don't want to be awake. So I will put today's notes for what they're worth onto the web, and I will also put some guidance for the remaining chapters. Let's see here. There we go. And so you can see here, there's I guess this is just, if I click on this, oops, it makes me sign in. Hold on. Oh, no, it should be signed in. And this goes to a page, and this page points to a PDF. And there's, a bunch of my own solutions. but this is a fairly limited set. And then I showed more on lecture on Tuesday. This is a stray light problem, you know. And then I showed a bunch more on Tuesday. Then I did a couple more yesterday, and so I'll just put them all on there as soon as I'm done with lecture here. So hopefully that'll be helpful to y'all. And I think that's about all I've got for today. Any objections if we break early? Like, oh no, Dr. T, I love hearing your voice. It's just like sticking a fork in my eye. Somebody has to object. Just kidding. Okay. So what do I say now? Go away. Bye-bye.
Dr. T,
Yes, Fook.
how many so we have Raman, crystal violet, HPLC, not UV vis,
And
Pepsi
fluorescence.
Coke, fluorescent. Okay.
Right. No,
I
no.
think-
HPLC and Diapepsi are the same. There's 4 experiments. Crystal violet, Raman,
Yeah.
HPLC of Diet Coke, and fluorescence of rhodamine 6G. Four experiments.
So that means that I've only need to do one more to go to lab one more time.
Oh, no. No. No, you have to come 7 more times.
Because I think I have the results for with the group, with my group for the other 3, I think.
I'm
write it
sorry,
down.
Fook. I'm sorry. You have
Okay.
to come at least 7 more times.
Okay. Okay.
I'm just kidding, of course. I'm just pulling your leg. I'm so tired. I don't know what's going on. But no. Yeah, just I don't know, come again someday, get some more data. You know,
Come on.
if you tell me, like, let's say, Fook, you stole someone's data for HPLC
No, I have
or
my own.
fluorescence or something.
Oh, no, I have my own.
Just hypothetically. Hypothetically.
Ooh, that never happened.
Just hypothetically. Okay. Let's say Cindy stole somebody's data, right?
Oh, not
You can agree with that, right?
not
Yeah.
Cindy.
Cindy doesn't have a
no.
choice because Dr. Terrell lost some of Cindy's data.
Oh, right. There you go.
So
So,
actually, I
Dr.
am
Terrell-
doing, yeah,
So,
a couple of labs with other people's data.
right. So, so long
I
as
can share
Cindy
with you,
tells
Luke,
me
if you
that
need
she's
to.
using, yeah. So long as you just tell me whose data you're stealing, I'm fine. You know,
Okay.
I don't really care. I don't, like, I want you to not be afraid of the instruments that we're using this semester, but there's, not a whole lot more we can learn, just kind of how to filter your samples and sort of get things ready. It's about all I can ask. So
Die the lab shock.
Are you going to tell
Anyway.
him how to get rhodamine 6G out? Do you want to tell him what you found works?
Oh, I sent an email. I don't know if you've seen it
Oh,
yet.
okay.
oh no, I
The
haven't seen
rhodamine
it.
comes out really well with alcohol.
Oh, it comes off the glassware? You mean
Well,
the
it comes
stains
off
come
of
off the glassware?
shoes and jeans. I expect it'll come off glassware on the floor too.
Oh, good. Excellent. All right, cool. That's very good to know.
It's a
Yeah.
nice trick too.
So next time that someone, yeah. Thank you.
So if you need me to go back in and clean up my spill, actually, I don't know if that was my spill or your spill.
Oh God, no.
That was our spill.
No. That's a red badge of courage right there. That's like, it's like we bleed for our chemistry. We leave big stains on the floor. Right, Nicholas?
Absolutely.
Absolutely. Okay. Alrighty, guys. So please bother me if you have any issues with the homework. And I promise, I absolutely promise, I will put the remainder of my work onto Canvas in this one homework chapter 20 notes. I'll improve this for April 22nd here.
What?
And yes, Fook.
What? Okay.
Yes.
Oh.
Yes.
Okay.
Chapter 20 notes. Exactly. These are all my solutions of the homework. I mean, it's not every problem, but it's the hard ones, I think. Hard ones for me anyway. Okay, guys. I think I'm done. I'm cooked. I will see everybody either today at lab or next week.
Thank
Take
you.
care.
Bye.
All right.
Thanks.
Thank you, Dr. T. Have a
Okay.
Thank you, Dr. T.
Bye. Ah.